We'll try and get started close to on time to give Phil as much time as we can. So welcome everybody. My name is Laura Haas. I'm the Dean of the College of Information and Computer Sciences at UMass Amherst. And as you know, our webinar today is why are AI systems racist, sexist, and generally unfair, and can we make them fair? With Assistant Professor of Computer Science, Philip Thomas. This webinar is part of our year-long series, Computing and Social Justice, which brings CICS researchers and the public together to critically assess how computing innovation intersects with vitally important issues like racism and bias, civic participation, economic inequality, and citizen privacy. Each webinar focuses on a different technology or application whose impact on society is extraordinary in ways that are both visible and invisible to the public. As computer scientists, we recognize that technology is central to the issues facing our country and hope this series helps to make its role more transparent. Today's talk will explore why artificial intelligence systems often exhibit undesirable behavior, from various types of bias to causing actual financial loss or delaying medical diagnoses. Typically, the burden of avoiding harmful behavior like this is placed on the user of the algorithm, who most often is not a computer scientist. Phil will share examples of AI systems that produce unfair behavior and discuss recent efforts to create new machine learning algorithms that can easily be applied fairly and responsibly in real-world applications. Please use the Q&A link at the bottom of the screen to ask questions at any time, and we will be answering them and discussing them after his talk. And now a little about our speaker. Philip Thomas is an assistant professor of computer science at UMass Amherst, where he co-directs the Autonomous Learning Lab. His research interests span reinforcement learning, decision-making, and safety and fairness in machine learning algorithms. Phil earned Bachelor of Science and Master's degrees at Case Western Reserve University and a PhD here at UMass Amherst. He joined the CICS faculty in 2017 after completing a postdoc at Carnegie Mellon University. He has published in the top AI conferences and journals, including publishing in the prestigious journal Science, and he's testified to the US House Committee on Financial Services Task Force on Artificial Intelligence just this year in 2020. Please welcome Phil Thomas.
Thanks. Just this year in 2020. It does feel like a continuation of 2020, yes. Anyway, thank you for the very nice introduction. And so, as Laura said, the title of the talk describes what I'll be talking about. And I made this, and then last night realized the talk was about an hour and a half, and so it had to be trimmed down a bit. And so I'm going to focus in the end more on the what does it mean for AI systems to be sexist, racist, and generally unfair? Why are they racist, sexist, and generally unfair? And then just a little bit about my work at the end. But that part about my work is the part that ended up being trimmed a bit. Okay, so let's delve in. Sorry, one second. There we go. So an overview of what I'll talk about. I'm going to start off by talking about why AI systems, or just arguing that AI systems have already produced unfair behavior. Then I'll give an illustrative example, just something concrete that we can dig into to really talk about this in detail, and that's predicting student GPAs from some of their application materials. Then I'll talk about something that we call impossibility results before talking about the sources of bias. So this is the why. Why is it that these machine learning systems can be unfair? Then I'll talk very briefly about some fairness research before ending with my favorite part of the talk, which is where I describe how everything that we talked about is wrong. Not incorrect, more ethically wrong. Okay, so sorry, the pictures are in the way of part of my slide. Let me move that. Great. So the claim I'd like to start off with is that AI systems have produced what some might call unfair behavior. And you might look at this and say that is a maze of hedge words. It's AI systems have produced what some who might call, why not would call, and why is unfair in quotes. And this is because we haven't defined what fairness means. And so right now we're just taking a very broad perspective in saying that systems have created behavior that some might consider unfair. And let's start off with a poem. So here's a poem called Gender. He is a soldier, she is a teacher. He's a doctor, she is a nurse. He is a writer, he is a dog. She is a nanny, it is a cat. He is a president, he is an entrepreneur. She is a singer, he is a student, he is a translator. He is hardworking, and she is lazy. So this was a poem. It was created by, I think, Vox.com, but using Google Translate. And the interesting thing they did is they went from Turkish to English. And in Turkish, the pronouns are all the same. They're all O. There's no separate he and she. And so Google Translate in its language model is filling in the pronouns here of he and she based on the assumptions that it's learned from the underlying data. And so some people might describe, especially some of these later ones, as some sexist behavior of this translation system. Another example is an article. This was originally from Bloomberg, but you'll find this reported in many different outlets, that Amazon has made some questionable decisions with respect to one-day delivery. So in the US, there are many different major cities where when you have Amazon Prime, you can get one-day delivery of items instead of the 2-day that we get out here in Western Mass. We're not considered a big enough city, but out in Boston, you can get one-day delivery from Prime. And what Bloomberg looked into was within city regions, which regions got one-day delivery and which ones are stuck with the 2-day delivery. So the blue regions are the regions where there is one-day delivery, and the white regions are the regions where people did not get one-day delivery. So you can see those labels there. And these are just various different cities if you want to see the areas, and you might notice a trend. So they plotted where people of different ethnicities live. So each green point here is, I think, 100 people who identify as white. And you'll notice we're just focusing on the Boston area. This gray part is where there is one-day delivery, and these white parts are where there isn't. This is water, so we can ignore that. But this one is Roxbury. And what you'll notice if you plot where people live that are more, where Black people live, each point here is 100 people who identify as Black. They are more concentrated in Roxbury. And this trend is not unique to Boston. So this is the city of Atlanta. In the north, it tends to be more white. In the south, it tends to be more Black. And there's one-day delivery in the north. So what happened is that Amazon made these decisions based on how many orders people were placing, how many people were Amazon Prime members, and various different statistics. And that resulted in this behavior where they were generally giving one-day delivery to white neighborhoods and not to Black neighborhoods. This was from, I believe, Joy Balwami's work, which was related to showing that facial recognition systems, actually this one was just guessing genders. So it's taking an image of a face and trying to predict the person's gender. These systems from Microsoft, Face++, and IBM have worse accuracy for people with darker skin than people with lighter skin, and worse accuracy for women than for men. And so this showed another bias in facial recognition systems, or I guess this is classification systems. Another example is Tay.ai, which is a strange name, but this was created by Microsoft. So Microsoft created this, it's essentially kind of like a chat bot, but in this case, it was a Twitter bot that would have tweets and conversations with people, and it would learn from the conversations that it had. So they say that the more you talk with Tay, the smarter it gets. And it started off with some nice expressions as you'd expect, but it quickly devolved into saying things that are clearly anti-Semitic. And this is, I think, one of the best examples, and it kicked off a lot of research in this space. This was an article by ProPublica, the news outlet, that looked at software that was used in 11 different states to predict who would commit a violent crime in the future. And this software was used by judges in 11 states when deciding during criminal sentencing. So when deciding what the penalty would be after someone was found guilty of a crime. And what ProPublica did is they broke all of the people that the software had made predictions for into different sets. So they looked at Black versus white, and the people who did go on to reoffend, commit a violent crime, and those who did not. And if we just focus on the people who did not reoffend, so these are people who did not go on, we now know later on, they did not go on to commit a violent crime. The system was more likely to label them as high risk of committing a violent crime if they were Black than if they were white. And this list goes on and on. There are endless examples that you can find in the news of AI and machine learning systems producing behavior that people might describe as unfair. Okay, so before we continue on, I think it helps to pick one example and really focus on it to see what is going on. And so for that, we're going to use data from this university, which is the University Federal Rio Grande do Sul, I believe. I'm probably butchering the pronunciation. where Brazil has a quota system where I think it was in 2012, it was mandated that half of students at federal universities had to come from poor neighborhoods or underrepresented groups. And as part of this quota system, this affirmative action system, they collected a lot of different statistics to show the impact that this had. And thankfully, we were able to acquire some of that data, which for this university included 9 different entrance exam scores that students had when they applied to university, along with their actual GPAs for the first 3 semesters that they were at UFERGS, and their gender. So this is what that data looks like. It's really simple. We have students' genders, their 9 exam scores, and then their actual GPA during those first 3 semesters. And that goes down to row 430304. So there are actually 43,303 students' data in this spreadsheet. 303 because the first row is just that title row. Okay, so now that we have some data that we could start to play with, we can ask, could we predict what students' GPAs are going to be from their entrance exams? And this is something that could be useful if we're trying to decide which applications to filter out, which applications should be looked at by a person. And this models many other real world problems that we face. Problems like which resumes should a human look at? Problems like which person should be given a loan, or how large of a loan do we expect someone would be able to repay? Okay, so let's plot this data. And we're going to see plots of this form a lot throughout this talk. The horizontal axis is always going to be the exam score. So this was the student score on this exam, and the vertical axis is their actual GPA. For simplicity, just with these plots, I'm focusing on one exam score so that we can visualize it really easily. So this happens to be the 3rd exam. And these are many circles. I don't know how well it's coming across on your end. These are many transparent circles stacked on top of each other to show the distribution of these 43,000 points, because without transparency, it would just all be covered. Okay, so given this trend, what we might do is try to predict from a new exam score what someone's GPA will be. And one way to do this is, for example, fit a line, right? Try to find the line that best fits this data. And if you find the line of best fit, technically this is the line that minimizes mean squared error. This line has an equation, y equals mx plus b. That's the y-intercept, or so y is not the y-intercept. Y is the output value. X is the input value, M is the slope of the line, and B is the y-intercept of the line. And these are the parameters of that best fit. So we could use this to try to make predictions in the future about what a new incoming student's GPA will be from their score on this exam. And what I would have liked to do back when I thought 30 minutes was endless, actually for a while I thought the talk was an hour, but even then we wouldn't have been able to do this, is a demo where we all interact and I show you, I would pull this up and show you this point. Say a new student has come to us and they've applied and this is their exam score. It's this blue mark on the axis. And we, the audience, get to make predictions about what they think these students' GPAs will be. But due to how long this takes and that we need to go through about 20 of these, instead I've just automated the process for us. But hopefully you can pretend that you, the audience, were making these predictions. And I'll tell you what we did. So I gave you a little more information. For each point, I found the students, the 100 students with the nearest exam score, and reported their average GPAs. And then I also gave the prediction from this linear fit. And what I've plugged in as a surrogate for your guesses as to what their GPAs would be are these nearest neighbor predictions. And so for this point, it was actually right on the line. For the next point, it was a little bit off, and this process repeats until we've labeled 20 different points with predictions. And the goal is that this is a nice baseline. We're not being biased. I think the audience to a talk of this sort should be very aware of the issues of bias. And so we would be able to do this in a fair way. And then what we can do is compare what the machine learning algorithms do to what we did to see what kind of bias are they creating that we don't have in what we do. So that was what I wish we could do. So pretend that we'd gone through that process, even though I just filled these in for us. So we've just made all of these predictions. This is wonderful. We can go to bed happy and content that we have created a bunch of predictions that are totally fair because we didn't have bias in the process of doing this. And we wake up in the morning to a wonderful newspaper clipping that says, Sexist audience attends talk. Yesterday, UMass Amherst hosted this talk. As part of this event, attendees predicted what GPAs would be. Turns out it's horribly biased in this study. And this is the key part. Specifically, attendees, really, this is just my stand-in for the attendees, overestimated the GPAs of male, this is cut off for me, sorry, give me a moment. The GPAs of male students on average by 0.38 GPA points, sorry, I'm distracted by different windows. Okay, 0.38 GPA points, and underestimated the GPAs of female students. Did I say predicted on the first and estimated on the second? No, I typed it correctly. Okay, so we overestimated by 0.38 GPA points on average for male students, and we underestimated by 0.22 GPA points on average for female students. And some might say that this is a form of bias. And I would have loved to do this as a demo to show that this isn't a rigged example. I am confident enough that whatever the audience does, it's going to show bias, because it's very hard not to be biased in these examples. So I hope you're not thinking, well, this is a case where these numbers were extreme. These are not extreme. Actually, when I manually went in and did this myself, I ended up with a bigger discrepancy. Okay, so what happened? Well, to see what happened, let's plot the same exact points, but color them by gender. And I know I'm sticking with stereotypes where I'm going to choose blue for male, but it'll just be easy for us to remember. So blue points here correspond to male applicants in our data set, and the red correspond to female applicants. The interesting thing is in the bottom right, these are people who got very high exam scores, but their GPAs were actually really bad. This is predominantly blue. It's predominantly male. Whereas the top left is predominantly red. Now this is a little bit deceptive because I actually plotted the blue points first and then the red points on top. If we plot the blue points second on top, this is what we get. So it's the exact same thing, just which one do we plot first? Which one overlays on the other one? And you can still see the top left tends to be red, whereas the bottom right is blue. So this is that trend that students who have lower exam scores but tend to have higher GPAs are more often women. And so this discrepancy is what was causing that unfairness. So to dig into that just a little more, this is a ton of data and it's hard to think about 43,000 points. So we can boil the issue down to this. Effectively, this is what's happening. We have 4 points just like this. And what we'd like to do is make predictions. And no matter what we do, actually, what is the point I want to make? No matter what we do, we are going to end up over predicting for men relative to women, right? We can fit a line and we are over predicting for the blue points and under predicting for the red points. We can try to fit whatever crazy curve we want. This is effectively unavoidable. So I will give you a moment to stare while I sip my caffeine and see if you can come up with any way to make predictions where it's each exam score maps to a prediction that is not on average over predicting for these blue points while under predicting for the red. Okay, hopefully all of you are sitting there thinking, of course, you can't do it. There's no way to do that in this example. And one thing that I should point out is this isn't just a problem. So on this data set, we fit a very simple line. Maybe it's the fact that we fit such a simple predictor to this data. What if we did something more sophisticated? So these are results from that exact same data set. This is a plot from the science paper. And what we're showing is the prediction error. So on average, how much did we overpredict for each gender? We have in white is female, in black is male. And this left set, LR, is standard linear regression, what we just talked about. But this one's actually doing linear regression on all 9 of the different exams. So it's this 9-dimensional problem. This middle one is deep learning. It's an artificial neural network. And you can see the same massive discrepancy in GPA predictions. 0.3 GPA points is a significant difference. And this one is a more classical machine learning technique called random forests. And all of them exhibit the exact same behavior. Okay, so you might be thinking, what if we consider gender though? Because back here, I said it's not possible to make predictions that aren't over predicting for blue and under predicting for red. But what if we condition our predictions on the color of the point, whether it is blue or whether it is red, whether the person is male or whether the person is female? So to dig into this, let's go back to the predictions that we made. And again, this would have been the green points for the predictions that the audience had made, but these are our stand-in. And for each of these points, I've also plotted where the actual student was that we were comparing to. So this green point here, if you can see my mouse, corresponds to our prediction for this student who happened to be male and happened to actually perform better. And what you'll notice, that bias, that fact that I had this news article saying that we were over predicting for men and under predicting for women, is because we tend to have more of these red points that are too high, that trend that we described before. So for these red points, we are under predicting with our predictions. And for these blue points, we are over predicting. So what if we consider gender? What if we did something like this? We look at a point and we say, if it's blue, if it corresponds to a male, we'll shift it down by 0.38 GPA points. Why 0.38? Because that was the amount that we were over predicting on average. So by subtracting that off, we'll now be predicting the right amount on average. And we can do the same thing for points that correspond to female applicants. We can shift their predictions up by 0.22 GPA points. So when we do this, again, the point is the average over prediction for men becomes 0, and the average over prediction for women becomes 0. So this is great. We've solved the fairness problem. Here you can see what that looks like. We're taking, so this prediction corresponds to a female applicant who was up here, and we've shifted it up. We're getting most of these red points closer to where they belong, and most of the blue points closer to where they belong as well. Okay, so great. We've fixed the issue of our predictions being unfair. We can now actually go to sleep content and happy with the fact that we've created this nice, fair classifier. And so we wake up in the morning and there's a new newspaper article. Same thing, but there's a difference here. So specifically, on average, the attendees gave 0.6314, so 0.6, it's a large amount of GPA points, higher predictions to female applicants relative to male applicants. So on average, just because someone is female, they are getting a prediction that is significantly higher than someone who is male. And this could also be deemed as sexist behavior. Okay, so you might be thinking, but that's kind of what we should expect in this case, right? So if you look at the data and take the average GPA of women in our data set across all 43,000 students, it's 2.9688. For men, it's 2.6139. So it is lower, and so it might be reasonable to say it's okay if the system is, quote, unfair in the sense that its average prediction for men is lower because their GPAs on average are lower in this case. But that's unique to this example. We can consider other very similar cases where this is not okay. So this is a report called Educational Redlining from the Student Borrower Protection Center that looked into what loan opportunities were given to students based on different properties, mainly which college they went to. So if you list that you went to Harvard versus Howard, Howard is a historically Black university, and maybe a college, I'm not sure. If you change only that in your application, it can result in a difference in the interest rates that you get. Basically, they might have behind the scenes a prediction of how big of a loan you'd be able to repay, and the predictions that they're making appear to be different depending on whether you went to Harvard or whether you went to Howard. And so this would be a case where blue and red correspond to which university you went to. And we might say that it is, in this case, racist behavior to on average predict something higher for points of one type. And if you want to look this up, this is reported pretty widely in the news. And the report has some really strong quotes like this one. Our findings from our broader analysis and the highlighted case studies are consistent, holding all these constant borrowers who attended community colleges, historically Black colleges and universities, and Hispanic serving institutions will pay significantly more for credit because of people's prejudices regarding those who sit next to them in the classroom. Okay, so I think we've established that AI systems have produced unfair behavior, and we now have an illustrative example where we've seen how this can happen because we tried making predictions, we saw that it was unfair, we tried correcting it, and we still saw that it was unfair. And this brings us to something called impossibility results. So going back to this case, imagine that I asked you to do the following. So I'm going to check the time. Time flies. I'd like you to predict, to find a way to predict what the GPAs would be from entrance exam scores. You can use gender if you'd like, but make sure that you're not being unfair in either of these two ways. So don't predict higher values for one gender, and don't over-predict more often for one gender and under-predict on average for the other, right? Are two different notions of fairness. And for the sake of time, I'm not going to stall too long here, other than to point out it's not possible. You might try to do something like fit separate lines for each point. This is great in that our average error for each point is 0, but we're predicting higher values on average for the red points, for in this case, women. So this is a case where for our data set, you cannot satisfy both of these notions of fairness simultaneously. One of them has to go. And this is a classic result in fairness. I think this paper is the best known for it, Inherent Trade-offs in the Fair Determination of Risk Scores, that starts to delve into what we call these impossibility results, pointing out that different notions of fairness can conflict to the point where it is impossible for a system to enforce certain ones simultaneously. If you're looking for more on this, there's a wonderful online free book called Fairness in Machine Learning, and their propositions 2 through 5 are a collection of these impossibility results, pointing out that different entire classes of fairness definitions cannot be satisfied simultaneously. And this brings me to, this is a quote from me when I had that chance to testify to Congress, which is on this point. It's, in any effort to regulate the use of machine learning to ensure fairness, a critical first step is to define precisely what fairness means. This may require recognizing that certain behaviors that appear to be unfair may necessarily be permissible in order to enable enforcement of a conflicting and more appropriate notion of fairness. And I think this is a point I really want to make clear. And it's something that back then I simply didn't have the time. And I think now we have that time to delve into what I'm really trying to say with this, which is issues like this may be conflicting with a different definition of fairness that is more appropriate. It may not be that the same average loan amounts should be given to people from Harvard and people from Howard in the interest of increasing social inequality, or, in the interest of increasing social equality, right? So it could be that this report is accusing this lender of producing unfair behavior when really they could be producing fair behavior with respect to a better notion of fairness, right? If we give people loans that they can't pay back in the interest of saying we give the same size loans on average to all different people, then we're hurting those people who can't pay them back in the long term because they can't pay back the loans and it's bad for them in the long term. So it could be that this definition of fairness that people are rightfully seemingly angry about is actually the right behavior for this lender to do if they were enforcing a different, more appropriate conflicting definition. And so when I say that these behaviors that appear unfair but may necessarily be permissible, we may need to look at this article and say, yes, this is the behavior that we would like to see. I'm hedging this with may. And to make this more concrete, just in case this is one of those points that I could see people disagreeing on, the notion of fairness that I think we should actually be enforcing is one that I'll talk about at the very end when I start talking about fig leaves. So, okay, that argument I just gave is an incredibly slippery slope though. So we need to be very careful with it. This is the argument that NorthPoint, so ProPublica is the news article that produced this analysis of predicting violent recidivism and the bias in those systems. They were analyzing NorthPoint software. NorthPoint published a response where they argued, we were enforcing a different notion of fairness. And it really didn't go over well because their notion of fairness seems less appropriate for this application. And it wasn't even clear that they were actually successfully enforcing that definition of fairness. Furthermore, you can use this argument for pretty much anything. You can argue that, yes, this behavior is unfair from your perspective, but from my notion of fairness, this behavior is satisfying this other different notion of fairness. And that is not necessarily a good argument on its own. So we need to be careful with it. So I want to delve a little bit more into the nuances of this argument. And I hate having slides that are just text, but we're going to have one. So first point, every decision-making system is going to be unfair from some perspective. There is some way to look at how it's making decisions and say that what it's doing isn't fair. So when we're accusing some system of being unfair, this is a system for giving loans, a system for deciding who gets into universities, any AI system, we need to make sure that there's an established notion of what fair means in that given context. So picture our two news articles. No matter how you make your decisions in our GPA prediction example, you get the most reasonable, fair group of humans we possibly can and have them make these decisions. We can write one of these two news articles because you cannot satisfy these simultaneously. And so a key thing is, from one of these perspectives, any way that you make decisions is going to seem unfair. So we need to pick one that is the appropriate one for this application and ensure that we're enforcing it. So that's what I mean by make sure there's an established notion of what fair means for that given context or application. So the next 2 points are on the opposite sides of this debate. Defense is now we're defending the person who's being accused of producing an unfair system. So when you hear about a system producing unfair behavior, I hope you'll check to see if the accusation includes discussion of conflicting definitions, that it says this definition of fairness that we're accusing them of violating is conflicting with these other ones, and we either check that they didn't enforce those other ones, or we have an argument why those are not appropriate for this application. And I think that is the perfect counter to this example. Let's flip to the other side. On the other side, when the accused claims innocence due to these conflicting definitions, we should check a few things. So we need to make sure that they're actually enforcing the definition of fairness that they claim they are enforcing. And then we need to also think which of these is right. For this application at hand, which is the definition of fairness that should take precedence? So in the GPA prediction one, it's probably the case that our first definition is a little bit more reasonable than the second. But I shouldn't weigh in too much on that for reasons I'll talk about on the next slide. Right, and this is for the point that we should not allow for arguments for clearly discriminatory behavior based on, well, I was enforcing some other poor definition of fairness. And the final thing is, for all of this, a key point is it's critical that we can agree upon what the right definition of fairness is for each of these applications. And I see something in the Q&A. I'm going to come back to those at the end just because I know I'm going to run super long with this. Okay. So what is the right definition of fairness then? We just said it's critical that we know which one is the right one. I don't know. I'm a computer scientist, and I'm very interested in the mathematical underpinnings of what it means to enforce different types of constraints on machine learning systems. But the social science aspect of this isn't something that I feel I'm any more qualified than anyone else to say what the right definition of fairness is. So for all of this, whenever I talk about one definition being better or worse than another, I want to emphasize that is purely my opinion. And I don't think my opinion on the right definition of fairness is any more informed than anyone else here's. Okay, so let's go on to what are the sources of bias? So we pointed out that systems can produce this unfair behavior. We pointed out that it's kind of tough to define what the right notion of fairness is. But once we've chosen a notion of fairness, why do systems sometimes violate them? Why do we have bias? So the first reason for bias, and there are probably more than three, but these are three general ones that I think are most common, is malicious intent. Someone intended for that bias to be there. That's the case with Tay.ai. Some of the bad things that it said were learned behaviors from the machine learning system, but a lot of it was people finding ways to manipulate the bot. So they found ways to get it to say any sentence they wanted to. And some of these may even be faked. I suspect this is one where they managed to get the bot to repeat any string they wanted to, and someone caused it to produce this output. So that can absolutely be one cause of unfair behavior. I think the most talked about one, and one of the easiest ones to understand, and I think it's overrepresented in the community, is this notion of biased data. So this is the idea that we live in a world that isn't fair. So if all of the data that's used to train these machine learning algorithms comes from this world that isn't fair, then why would we expect the model that comes out to not reflect those exact same unfair biases? And so we can summarize this with the saying, garbage in, garbage out, or the thing about data is garbage in, garbage out. Another way of putting it is, if there's some sort of bias in the stuff that we put into our machine learning algorithm, of course we should expect it to exhibit some related bias on the other end. And this is a very common form of bias. I believe one of the previous talks was by Mohit, and in natural language processing and computer vision, this is probably one of the bigger sources of bias. But the one that I think is really fascinating is the third. And that's not biased data, but it's biased algorithms. It's when the machine learning algorithm itself injects unfairness into the decisions that it makes. So going back to our example, remember when we made these predictions, we said that we were over or under predicting on average. We were over predicting or under predicting on average relative to the exact same data set that we were using to train. So we were over and under predicting, not relative to some ground truth where there could be bias in the data relative to ground truth. So we have the real world, then we have biased data, and our predictions are biased even relative to the data that we've been training on. So, sorry, I've got another window in the way. So the additional bias that we've seen is added by the machine learning algorithm on top of any bias in the data. So I think this is a perfect case showing that machine learning algorithms can inject unfair behavior. And moreover, I think they almost always do. This is very, very common. So why do algorithms inject their own bias? It's not because we coded them up to be that way. It's not that we said, I want this algorithm to be biased, I'm going to create bias within the algorithm. Even when we try not to, we end up with bias. And the core underlying reason is conflicting objectives. So to get to this, think about the following. What if I said, I want to drive to Boston as fast as possible, but I want to stop at the red lights? These are conflicting objectives. Drive to Boston as fast as possible means never let off the gas. But stopping at the red lights means I'm not actually going as fast as possible. I'm just going very fast, but I am going to slow down a bit. What if I want to, this is not a great example. Let's move to the next one. I want to order the tastiest food. Okay, so I'm ordering all of the cheesecakes on the menu, right? But don't make future me unhappy. Well, then I'm having decaf coffee, right? So the optimal solution changes when you put these constraints on that are conflicting with that primary objective. So jail as many murderers as possible. Okay, we throw everyone in jail, solved. But don't jail innocent people. Okay, well then some murderers probably won't be put in jail because we won't have enough certainty that they were the person who committed the murder. Another one, make predictions that are as accurate as possible, but make sure that they're fair. The exact same issue is here. These are conflicting objectives. In order to make fair predictions, you usually can't make predictions as accurately as possible. You need to back off a little bit from being accurate in order to consider fairness. And so we need to ingrain notions of fairness into our algorithms and tell them, your objective is not just the primary objective of predictive accuracy. We also have fairness constraints on top. Okay, so now a very brief overview of fairness research. This is like 2 slides in 2 minutes tops. The main thing I want to point out is that the machine learning community is absolutely aware of this, and I think the fastest growing field right now is probably fairness within computer science. Across all the different subfields of computer science, fairness is a hot topic. There's a new conference, Fact Star, that is growing in popularity. And at the 2 conferences I consider most, ICML and Europe's, there are explicit mentions of fairness as topics of interest within the calls for papers. So this is a booming area within machine learning. And the specific angle that I take on this is Seldonian algorithms. And this is that science paper that Laura mentioned. And what Seldonian algorithms do is the following. The first thing, and this is actually what differentiates them the most from other fairness-aware algorithms, is that they let the user define fairness. And this stems from that previous slide. I don't know what the right definition of fairness is, especially because I don't know how someone's going to use the machine learning algorithms that we create. If they're using it for loans, the definition of fairness might be different from if they're using it to decide who gets the free upgrade in seats on an airplane to who gets into university. These all may have different notions of what it means to be fair, and there may be some applications where none of the existing definitions are applicable. And for those, we need to give the user the freedom to say, for their application, what is the right notion of fairness? The second thing is that we allow the user to pick the probability P. And then what Seldonian algorithms do is they guarantee that with that probability P, they will not produce unfair models, or in general terms, unfair decision-making rules, where here unfair is the definition that was provided by the user. So we create the algorithm, and then the person using the algorithm subsequently defines fairness. And that means the algorithm has to have a way of parsing users' definitions of fairness, reasoning about what causes that unfair behavior, and then automatically avoiding it. And this was the work in science. And on top of the GPA prediction examples that I already showed, we also considered 5 standard definitions of fairness. So if some of you in the audience live in the fairness space, you'll know that regression, which is this line fitting example, isn't the most common case. Classification is much more common. And in that setting, these are 5 of the most popular definitions of fairness. And we showed that our system was able to enforce constraints with respect to all of them, whereas none of the other algorithms that we know of are able to handle all of these different definitions of fairness. And actually, this plot that I showed earlier was from that paper. And not to say that this definition of fairness is right for this problem, but if someone chose that definition and said, I want the difference in these bars to be between these red lines, that's something that our algorithm was able to do. Okay, so what are our current and past research projects along this vein? So some recent projects include the following. One question is, can we make our guarantees robust to demographic shift? This is the idea that what if I train a model in California and then I deploy it in Boston? I know that there are differences in demographics. There will be more people of different ethnicities and genders between the two cities. And when that shift happens, fairness guarantees can be violated. A model, a system that is fair in LA may not be fair in Boston. So how can we automatically take models and ensure that even though they were trained in California, if I know I'm deploying them in Massachusetts, I want it to be fair in Massachusetts? And that is something that we are submitting hopefully next week to ICML. Can we make fairness guarantees robust to general distribution shift? So this is the question of, what if we don't know that it's just demographics, things like race or gender that are changing, but we just know that in general, the distribution of people has changed from training time to deployment time. And this is a very common issue, that the world is constantly changing over time. And when we collected our training data, the world was different from what it will be when we actually deploy the system. And we want the system to be true, not to be true, to be fair when we deploy it, not necessarily when we trained it. Can we make these guarantees robust to adversarial data corruptions? So another issue is, what happens if in the gathering of our data, there's a mistake? Someone writes the wrong thing and that's parsed incorrectly, and the end result is some data points are wrong. The guarantees that we have can be completely violated. And so these fairness guarantees are very brittle in that sense. And so what we've done is some work. This was by Pinar at the last NeurIPS conference, I believe. We showed how we can make our algorithms robust, even if an adversary was coming in and deliberately perturbing our data to force us to draw the wrong conclusions. So if we're robust to that adversary, then we're also robust to those accidental mistakes in data collection. Another question we consider is, can we achieve the same fairness guarantees with less data? So this is the question of, can we do everything we're doing just more efficiently? And this is really the core statistical question. I'm not sure if Eric Lerner-Miller is here, but he and I work on constructing confidence intervals for different statistics. And for me, the motivation behind that is exactly this. Another question is, can we enforce these guarantees in other machine learning settings? So I've talked about regression, where you're fitting a curve. We talked about classification, but we've also done this in contextual bandit and reinforcement learning settings. And lastly, can we broaden the set of definitions of fairness that these are compatible with? I do want to say this was the work of fantastic collaborators. So there are actually many more than on this screen. And this is not just me, there are many people contributing to this line of work. Okay, so on to the last part of the talk, where I describe how everything that we talked about is wrong. So I'd like to talk about Lawrence Sherman. This is a story. I took one criminology class long ago as an undergrad, and the only thing I remember was this story. And it really stuck with me. This was a criminology professor who in the 80s ran a study. It was the Minneapolis domestic violence experiment, looking into the impact of mandatory arrests on domestic violence. So the interesting part of this is right here. The study called for officers to randomly select a third of offenders. This is when they're responding to a domestic violence call. And 1/3 of them are just arrested no matter what. 1/3 are getting counseling, and 1/3 are being separated from the domestic partner. And they found that the 1/3 where the people were arrested resulted in some improved outcomes. And this last part is very interesting too. The results of the study showing a deterrent effect for arrest, meaning there's less domestic violence as a result, had a virtually unprecedented impact in changing then current police practices. Subsequently, numerous states in this case was 25 states put in place laws that mandatory arrests are in place for domestic violence calls. That means if police are called out and there's evidence of domestic violence, they have no say in it. They will arrest whoever seems to have hit or hurt the other person. And now I'd like to show you a YouTube video. Give me just a moment. Of Lawrence more recently. So I'm giving it away a little bit. It turns out that this was a horrible policy, that this was bad in almost every metric that they could come up with. And since then, Lawrence Sherman has spent much of his career trying to undo exactly the quote progress that he had fought for originally. So let me share one moment. That's the wrong button. Share this, optimize for video clip. Okay, so we're just gonna watch to the end. So this will be a 5-minute clip.
high-end harm. But what has happened in the time period since the commission is this focus on the three choices that they made that led to the Minneapolis domestic violence arrest experiment in 1984 that, unlucky for the science of external validity, happened to be done in a low unemployment town where arrest had a deterrent effect that was not replicated in other communities with much higher unemployment rates, later understood better by looking at the moderator effect of unemployment on the recidivism of people arrested for domestic violence, which showed that arrest works pretty well to deter people who have jobs from having repeat domestic violence, and it doubles the rate of domestic violence for unemployed people who are arrested. That was something that the NIJ's randomized controlled trials funded in Milwaukee and in Omaha and in Miami showed very clearly, strikingly so because the three different demographic groups, predominantly African American in Milwaukee, predominantly Hispanic in Miami, and predominantly white working class in Omaha, were so different, and yet the moderator effects with respect to employment showed almost identical patterns. So why is the focus on that choice, which led, after the Minneapolis experiment, sadly, to 28 unrepealable laws across the 50 states requiring the police to make arrests whenever they see evidence that a misdemeanor domestic violence case has occurred, the only misdemeanor for which that's true under the U.S. legal system? And I think to ask why that's not good enough for victims, why it's not really focused on the question of helping victims, we only need to point to the long-term death rates of victims whose abusers were arrested in Milwaukee, who were 64% more likely to die of heart attacks, cancer, and other causes than the same kinds of people in a randomized trial of 1,113 victims whose partners were either arrested or warned. The warned victims were more likely to be alive. They had half the death rate if they were African American when their partners were warned that they had if the partners had been arrested. So why does this victim-unfriendly, in fact, victim-high-harm policy persist? And my answer is that it's a fig leaf. It's a fig leaf against the true target, which is the 5 women a day who are getting murdered. And in relation to claims that have been made that mandatory arrest prevents murder. And yet with the 23-year follow-up in Milwaukee, we found that out of those 1,100-some victims, only 3 of them had been murdered in exactly the same proportion as arrest and warning had been administered. So very low base rate and no difference between the treatment outcomes. Absolutely no evidence that mandatory arrest has a preventive effect on homicide. Strong evidence that it increases mortality for other reasons. At the state level, Iyengar has suggested that murders of women go up when mandatory arrest is imposed. You can't touch the mandatory arrest issue because it is a fig leaf against these women getting killed. But key question that nobody ever asked, how many of them had had prior contact with the police? And the answer in the United States, in the United Kingdom, in Australia, is consistently that the women who are getting killed are not women who have previously come to police attention with that partner, in the vast majority of the cases. So the idea that the police can prevent murder by making arrests at the prior stage before it escalates, and incidentally, all of the systematic studies with large cohorts, up to 300,000 now in Kent, Constabulary in England, shows there is no escalation. The escalation is a myth. It's something that came out of clinical research, not systematic sampling of the kind that the Commission pioneered in so many other areas. The area of domestic abuse has not only resulted in all of the harms that I've mentioned, but it has put a huge number of women in jail and in some cases in prison in what's called mutual combat arrests by the police, whose response to mandatory arrest has been to arrest both parties. And that has not helped anybody. It hasn't helped the police legitimacy crisis. The very high proportion of black males have been arrested in inner cities for domestic abuse. I think the commission that we hope will occur needs to consider not only the specific issue of the future of domestic violence research and policy, but the need to link much better targeting research to the inventory of tests to be done that can then inform the tracking to see whether we're actually making progress. Because at this point, I'd have to say, we don't have any evidence that progress has occurred. In some ways, I'm inclined to believe that we've only made things worse. Thank you very much.
Okay. Sorry, let me switch back. There are only a couple more slides. I know I'm over time. Sorry, Laura. Okay, back to PowerPoint. Great. Hopefully you can all see my PowerPoint slides now. So I think this was a fantastic example of what I'm worried is going to happen in fairness work, where this was a man who started his career with the right intentions and trying to do the right thing, and ended up putting into place a system that he spent the rest of his time trying to undo, in a sense. And a fig leaf is the perfect example for this. So for anyone who hasn't seen this use of it, it's a metaphorical expression meaning a flimsy or minimal cover for anything or behavior that might be considered shameful, with the implication that the cover is only a token gesture and the truth is obvious to anyone who, and the rest is hidden behind my thing. So the point is, it's something that feels like it's making the issue better, but underneath it's really not. So let's go back to our fairness definitions and let's look at just some of them. Let's say fairness definition number 1 for giving loans. I want the system to be able to say I was equally likely to give loans to Black and white people. Another definition, of the people who would repay their loans, I was equally likely to give them a loan, regardless of race. Another possible definition is I did not consider race when deciding who to give a loan. Another possible, I thought there was another one, but there isn't. I would argue that all of these are short-term notions of fairness. They are fig leaf definitions of fairness. They help us to feel good and feel like we've done something about this issue, but they're not actually combating the real issue of existing social inequality. So the competitor for this is what's called delayed impact. So this would be a definition of this other form, which is the automated loan approval system makes choices that reduce a variety of measures of racial inequality over 10 to 50 years. So can we make decisions that will reduce social inequality? And remember this concept of conflicting objectives. These first definitions are likely conflicting with this later definition. So enforcing these notions of we were more likely to give loans to someone in a certain setting, or we on average predicted higher GPAs for people of one gender. These definitions are, I believe, fig leaf definitions, and what we really should be caring about is delayed impact. And I worry that these fig leaf definitions can take off and become popular because they are superficially appealing, like the notion of we should just arrest everyone who commits domestic abuse without giving any possible consideration to the police officer on the scene. So if you want to learn more about delayed impact, there's a fantastic paper. It was the best paper at ICML, I believe, 2 or 3 years ago, titled Delayed Impact of Fair Machine Learning by these authors. And this paper delves not into how do we possibly enforce delayed impact notions of fairness, but just pointing out that standard definitions of fairness are not necessarily related to delayed impact. And you can enforce many of these standard definitions of fairness, and the delayed impact could be positive or negative. So something I will add to this list, a project that's in progress with Bruno Castro da Silva and 2 students, Blossom Matevier and Eleni, is trying to work out, can we enforce delayed impact fairness definitions? And I do believe that we can. There are a few challenges left, but that is what we are actively working on at the moment. And so with that, I will wrap up. My apologies, Laura, for going way over time.
Sorry about that. I was on mute. No, I'd like to thank you, Phil. That was a fascinating and really broad talk, and most of the audience has stuck with us till the end. So I have a couple of questions queued up. Other audience members who may have questions, please remember to use the Q&A tool on the right of that bottom panel there, and we will get to them as we go. So Phil, question number 1 comes from Tristan Warnica, who asks, would you consider incomplete data to be a source of bias in data? He's more looking at the inability to fully model the real world in statistics or finite sources of data. i.e. people are more than their test scores, than at other possible definitions of incomplete?
So sorry, I'm realizing as this is up, and I will absolutely answer this. I didn't leave up my end slide. My end slide had on it a quote from Lawrence Sherman. And it's the quote that he had at the end of that talk, which I wanted to say I really hope is not the quote that I'm going to have to give 30 years from now about the fairness community. And that is, in some ways, I'm inclined to believe that we've only made things worse. I think it's an incredibly powerful statement that he ended with that. And it's something the entire fairness community should really be thinking hard about. Anyway, on to this question. It's a great question. So is incomplete data a source of bias in data? You'll notice that throughout the talk, I put bias in quotes a lot. And that's because bias means different things to different people. I am heavily biased, to use the word biased. I'm heavily biased on this question by coming from a machine learning background, where to me, bias means something very specific that is not unique to fairness. So whether or not I would use the semantics of the word bias in this context, I don't think is particularly relevant, whether I would use that word. Is it reasonable to call it bias? Yes, I think it would be reasonable to say that incomplete data could be a source of bias in the data that results in unfair behavior. Adding to that, this question said, looking to real world statistics. So another point I would like to make is the algorithms that we've created, the Seldonian algorithms that we created that I've only very briefly mentioned, they're actually robust to bias in the data. They're robust to incomplete data in the sense that as long as the distribution of data that they see at training time and testing time have the exact same bias in them, they will still remain fair. So they'll enforce their fairness guarantees given biased data. But the end result of this is if you give them data that is biased when you train, and then you find out a way to make your system, your pipeline of generating data more fair. So maybe within this, there's a natural language processing component that doesn't work as well for certain dialects. Right? And you improve that so that it works equally well and better for these other less common dialects. That could actually result in our system becoming unfair because we're working under the assumption that the distribution of data and training time and testing time is generally the same. Hopefully that answers the question. If not, I'm happy to take a follow-up on that.
Okay, so our second one is a good controversial question. Abhirup Mukherjee wants to know, what do you think of Google's treatment of Timnit Gebru? And how do we take equity and fairness more seriously as a community when the messaging from top companies and researchers can be so mixed?
So I don't know enough about what happened to have an informed opinion on it. I have friends who have not come out in support of Timnit at Google, which surprised me. I would have assumed that everyone would. And it tells me that I don't know enough to really have an opinion on this matter. So I don't think I can really comment on the Timnit case. There was a second part to this. Unfortunately, I see the questions now in the answer tab. The second part to the question was something about, oh no, sorry, I can't find it.
Yeah, I'll tell you.
Oh, there it is. I see it. So how do we take equality fairness when the messaging for top companies and researchers can be so mixed? I think the messaging from researchers in academia is pretty consistent. The messaging from industry is a little concerning. I don't find it particularly surprising that industry has some of these biases. I think it would be very surprising if they were the upstanding, fantastic institutions that we hope they would be. So how do we take this research seriously? Well, we can absolutely take the research seriously, and we should hold the companies responsible when they do something that's wrong. We hold them accountable when they do something that we view as unfair. And when I say that, that's not a piece of this is things like a firing of a person, but more when they produce systems that are unfair, they should face the consequences of it. So a good example is ProPublica's article about Northpoint. It was really bad for Northpoint when ProPublica pointed out that they were producing unfair predictions. And I don't believe Northpoint is around anymore.
That's great. We have no more open questions at this time. So unless something pops up very soon, I'm going to thank Phil one more time. That was a great talk. You've left us all speechless and very, very how should I put it? I at least feel a little less confident and sure after all of that. So
Yeah.
that would be kind of my point. We did just get a question that came in from Dan Lee, who asks, how do we deal with conflicting objectives?
Yes, so there are many different ways to deal with conflicting objectives in the general case. I'll answer this in the context of fairness and machine learning models that are enforcing fairness guarantees. I guess one of the points that's important is, as a computer scientist, I think it's our job to make sure that the systems that we create make it easy for other people to control their behavior, right? So that a social scientist can come in and say, this is the appropriate way to properly balance accuracy with fairness constraints. And we should have a mechanism that allows them to put those constraints on the algorithm. So a big part of my focus on this is trying to figure out how to make algorithms that give users this ability to put their own definitions in, so that when someone who is more informed, when someone who has a better sense of how to make these trade-offs comes along, they can put that into the system. I guess I should say, I don't view myself as an expert in fairness. I view myself as an expert in machine learning and create machine learning systems, and then thinking about how they could interact with different types of guarantees, like fairness guarantees. So a point along that line is the science paper. We use the exact same techniques to prevent sexist behavior in the GPA prediction task as we did to prevent dangerously low blood sugar levels, hypoglycemia, in a type 1 diabetes treatment example, which has nothing to do with race or gender or inequality. It was just a safety constraint. So the underlying technology was the same. It was the question of, how do we let someone specify undesirable behaviors? In one case, fairness that they want to preclude. In another case, dangerously low blood sugar. And the machine learning algorithm can understand that and then enforce that guarantee. So with all of that hedging that I'm not really a fairness person, personally, what I think we need are hard constraints on fairness, and then precision should be maximized subject to those hard constraints on fairness. So there should be rules, like if you like the 80% rule, saying that we can hire in any way you want to maximize your company's profitability, but you have to satisfy the 80% rule. So something where we have a hard constraint due to fairness, and subject to that, we try to optimize the primary objective.
Okay, there's some, I just want to make sure that everybody saw the chat question, which isn't for you, Phil. But this is, where can we access the recordings of these talks? Obviously, you have a few folks who would like to go back and study some of this at leisure. They are also asking about slides, if you consent. And the answer on the recording is, attendees will get this, this recording next week. We typically usually also post it on our website. Eventually, we can make sure that when we say we're sending, I think it goes up on our website and we send you the link. I'll leave it to Phil if he wants to provide slides up there as well.
I'd be happy to.
Great. Okay, well, with all that, I would just like to thank all of the audience for coming and for hanging in there, and a great discussion. And again, Phil, thank you so much for the thought-provoking talk. And Phil, please make sure you read the answered questions. There's one in there that was for you.
Will do.
Okay.
Thanks.
Bye-bye, everybody.